Hi everyone. Today we'll have the third part of our seminar series. And today's lectures will be about the doubly robust estimators, importance sampling based estimators, and conditional AT based estimators. And Karthikeyan, if we have time, also may discuss some open problems related to these areas. Thank you.
Yeah. Okay, so I'll just do a recap because it's been some time. And then so last time people asked, okay, you're just deriving equality into equality. People wanted some concentration bound. So you'll see one today. And then I'll just go on to, again, deriving more estimators because this course will at least be for the next 1 or 2 lectures, be more about identifiability. Okay, so recap. Under the standard assumptions, which is ignorability plus positivity primarily, of course, consistency. Consistency simply means that you have these two hypothetical columns, and depending on which treatment you do, you basically substitute one or the other from the other column. That's consistency. Positivity says that for every person, there's a non-trivial probability that you would assign either of the treatments. Ignorability basically means effectively there's no confounder, but it's this complicated equation. I'll just write it as YA of U is not YP. So Y small t of U is independent of capital T given X. So for both the treatments, the potential outcome is independent of the treatment given X. Okay. So under these three conditions, we basically saw multiple estimators. So the first estimator is that the expected value of, let's say, Y, let's call it T, right? So YT is nothing but the expected value of, again, another expectation, Y given capital T is equal to T comma X. I'm just writing a more general quantity, right? So this was basically the regression estimate, or it's called standardization, or controlling for X here, right? Now the second estimator was importance sampling based. Here, what we said was the potential outcome is nothing but the expected value of T. So I'm assuming binary treatment. So if you want, I'll just do indicator. T is equal to small t times Y divided by the probability of T given X. Right? So this is our second estimate. So we said variance is high, bias 0. Okay. So then we saw IISc estimator. Which is given by again, the same thing. The left-hand side remains the same. We said that without Y, this quantity is 1. That's what we proved last time. And the IISc estimator would basically simply be the expected value of indicator that T is equal to T times Y divided by probability of T given X divided by just everything without T, Y, right? So if I get an empirical estimate of this, consider these to be W of X, the weight functions. So this is just weighing the treatment samples and the control samples essentially by a weight, and it's just sort of doing a very simple regression, right? That's what we saw. And the variance of this estimator is very well controlled. In fact, it's bounded, but bias goes to 0 only asymptotically. And it to right? This is what we saw. Then there was a fourth estimator where we said we don't know whether we can ever estimate P correctly, nor to do the regression properly in a consistent way. In which case, if at least one of them is very good, you might want to take advantage of both. So that's the doubly robust estimator. So I think I have to stay on this side of the board, right? So let's do it. Let me actually.
We can draw a line there.
No, you can use both.
Use both. Okay. Okay. So doubly robust estimator. That's the fourth one. So what we said here was let the regression estimate be V of X. So V of P, let's call it V hat of X. This is basically an estimate of the expected value of Y given P is equal to 1 given X. Then we said Y hat of X will be an estimate of let's say P of P is equal to 1 given X, right? Now what we said was the estimator is given by the expected value of Y1 can be estimated by, I'll just write it as an expectation inside. All I meant is just use these estimators and just average, but I'll replace the average by expectation. Okay, just saying that n tends to infinity, I want to understand what happens. And let's say I don't care about the finite sample. Or if you want, I'll just write summation here, to be very clear. So this would be the V hat of X plus you take the residue between Y and this V hat of X, and then you import a sample, right? Because you have captured some amount of signal, but you just don't know if it's unbiased or not. So what you do is you take the residue and just do import sample, right? So that's a simple trick, and that will basically give P is equal to 1 divided by Y hat of X times Y minus V hat of X. Okay, so we stop here, and I made a claim that if V hat of X goes to this as n tends to infinity, or Y hat of X goes to P of T given 1 given X when n tends to infinity, this estimator will have 0 bias. That's exactly my statement, right? So let's actually manipulate these expressions to see why that is the case. It's not very difficult. You just have to, yes. Yeah.
So on these four estimators, right, our goal is to estimate expected value of Y of T.
Always yes. Y of 1, let's, yeah, Y of T.
Right. So our goal is to find expected value of Y of T for T equals 0 or 1. Right. So you have these different estimators. Right. So whether one of them is better than the other will in some sense be dependent either on the sample complexity or the convergence. Right. Just because their variance is high or low.
Yeah.
Right?
True. I'm just giving you different trade-off. In some cases, maybe you actually find it's over here. Here, maybe you should go for. Here, saying is that in some cases samples are very low, so variance matters a lot more. Therefore, you would rather have a small bias, but then you would want variance to be bounded. In fact, variance here is bounded by 1, right? So it's just merely a trade-off. What I'm saying is doubly robust will definitely be any day better than these two, because you only need consistency.
So better in what?
Because let's say the bias here is not 0 yet, but going to 0. You are only doing important sampling on the bias. And the rest of them is what it is, essentially. So this will have bias. So if you have a good estimator for pi hat, then you should be using it. Of course, if everything is noisy, this can add more noise. I completely agree with that. If one of them is consistent, or you expect one estimator, pi hat or B hat of X to be very good, then you would rather use this.
This competition is more expensive.
I mean, the estimator itself is just same thing, right? Like there's nothing complicated over. Oh yeah, yes. Of course, you have to estimate regression, and then you have to do classification, and then you have to decide which. I will derive because people were requesting concentration results. So we will see a median of mean. Confidence interval. And there's some assumptions. So you can derive confidence intervals, but I'll tell you how bad it is. It will exactly be a function of the variance. And I'll tell you what variance what matters for a particular. Okay, first, let's finish this. People, yeah,
It is always better.
it is true. Yes. Sometimes if you have your pi hat effects to be super bad, then it doesn't make sense, even if the bias is very small, it doesn't make sense to import and sample with something that is so horrible.
So asymptotically always use doubly robust, but finite depends.
Depends, but at least from a consistency point of view, you only need one of them to be good, and then you're usually fine. So that's what it is, right?
There's some lower bounds already available.
So there is a lower bound. Well, if you so from heavy-tailed estimation literature, there's a lower bound on the confidence interval. You can't do better than that. But are you saying if there is a lower bound for what's the best estimator? I think there was a paper by Microsoft that exactly answered your question, and the answer was some type of doubly robust estimator, some variant of this. In fact, what you can do here is that each one of them by itself, I mean, this is one term, right? Now you can take a weighted version of this plus any of them, and that would also be an estimator. And it turns out that if you tweak the weights correctly, the best minimax rate is achieved by one such estimator. Okay, and that was formally proven by one paper from Microsoft Research. I just don't know exactly what the paper is because you asked this question, it came to my mind. But there was an exact characterization. Yeah. So something with doubly robust is necessary to achieve minimax of it.
And those weights, you can estimate those weights also.
Correct. What exactly do they do to estimate that? I think it was
data dependent.
Yeah, you can make it data dependent. Correct. It is data dependent.
Yeah, it is data dependent, but you have to know those weights to achieve that.
Yeah, so there's a way to compute those. They say that there exist some weights to W of X such that it achieves the minimax guarantee. That's all I can say. But whether you can compute it in finite samples, those estimation errors, I don't know.
Also, the bias in the third estimator can be
Bounded.
It is in finite samples. It will be some. There will be some upper bound you can show. Is there some that upper bound? Is there some relation to the variance in the second?
Correct. So I can give you a confidence interval of both. Here, the ratio you have to work with the confidence interval to see what is that. So, for example, I can give you a lower bound. Both of same variance. Because by default, we are using less than one. In that particular case, it will be exactly controlled by this variance. So you could potentially get a confidence interval. But again, the question is, what's the tightest you can get? That again is separate issue. And people have analyzed self-analyzed one. Okay. So let me first tell you why we believe this is consistent, and then we can go ahead and work through concentration results for this. I'll show you median of each estimator. But it's very, very related to heavy tail estimation in general. There's nothing very specific about important sampling, but one place where it's often used is in important sampling. Okay. So
Why are you talking about heavy tail? What is heavy tail?
So 1/p of t given x. Let's say I don't even have a bound on this. I mean, I know that it's greater than 0 for all x, but the point is that you could have a sequence maybe tending to 0 or something very, very close to 0. So this could have a very bad upper bound, 1/p. Right? So technically, for all practical purposes, the tail could be very heavy, right, within that particular support. And you can extend the support as much as you want. But what we can say is that 1/p square has some variance. So or some first moment is actually, or second 2 plus epsilon moment is bounded. If that's the only thing I give you, then you can still get a sub-Gaussian type concentration. But the estimator will not be this. It's not summation. It will be different. And I'll come to that. It's median. It's a very standard trick. Is that clear? So all I'm saying is that the only thing I know about this 1/p is some moment. Nothing else I know. I have no idea about the CDF, no idea about the distribution. I cannot claim it's sub-Gaussian. I can't claim anything. All I have is variance. Then what do you get? That's what we do. I mean, I'm cheating a little bit. I said subgaussian take on. There's a little bit of a subtle message there. Once I show you the estimator, you will understand what that subtle message is. So depending on the confidence you want, you need to change the estimator. But usually in like just mean estimation, the estimator is always fixed. Only your tail bounds vary depending on what you want, what deviation you want. But here you have to be very careful. The deviation that you want is coupled to the estimator. So you can't get one estimator that has uniform tails. For different things, for different deviations, I need to change something in my grouping, for example. Right. So depending on the confidence I want, I need to change something in my estimator. But in normal, usual mean estimation, that's not the case. When people derive concentration bounds and they just do summation x by n for all delta, for all confidence interval, you can always derive a tail bound. The estimator doesn't change. But here you have to like, sacrifice on that. So we will see that also. And there are some very interesting open problems. I'll tell you about those two. Okay. So let's get back to Doubly Robust estimator. So only thing I want to claim is that in some sense it's some best of both worlds. So let me just convince you that it is the case. So what you're going to do is that we will call this, so the expected value of this. Okay, so let me write my estimate. Let me call this as the Doubly Robust estimate, right, of y1. I don't mean that I have an unbiased estimator. I'm just taking expected value of this estimator over x, okay, asymptotically, right, minus the true expected value of potential outcome. What is going to be this, right? Now, before we manipulate this, I want to first tell you that the expected value of y1 by this argument, first argument, is already nothing but the expected value of b star. And here I'm taking an estimate only with respect to t is equal to 1. And this is like the optimal estimate. So let's call this b star of x. Okay. So the expected value is exactly given by this optimal regressor. If you could find it, this is exactly you just have to average over all. Because already it is conditioned on the treatment you want is just a simple regression, right? So there is some regressor, but we don't know what that regressor is. All we have is access is b hat and okay. Now there's also a phi star, which is true P of t, not the estimate. Okay, these two are estimates, these two are true quantities, right? Now the interesting thing is that this expected value of y1 is also equal to, we have already seen that this is nothing but the indicator t is equal to 1. We write it as t, I'll assume binary here, simple, p times y divided by phi star. So it's equal to p star, it's also equal to this, right? So you can always substitute one after the other. Okay. So now let's write this estimator in terms of these quantities and basically see what actually happens. Okay. So the first thing what I'll do is that we have already said by consistency that the indicator of t is equal to 1 times y can be always replaced by indicator of t is equal to 1 times y1. So we'll do that. Okay. So we have the expected value of b hat. I won't write the x's, right? So times indicator t is equal to 1 by phi hat. Okay. Times so I said that 1 times y is nothing but y1, right? And if you condition on x, I can do whatever property. So if I condition on x, y1 is again equal to b star of x. Right? y1 of x is equal to b star of x. Therefore, indicator times t is equal to 1 times y is equal to indicator times t is equal to 1 y1. y1 again can be replaced by b star of x. So I'll do all of the substitutions. So essentially, all I have is b star of x here. Minus b hat of x. Here, I've done many things. So the first thing I have done is the expected value of y1 conditioned on x is equal to b star of x. This is one thing I've used. The other thing I've used is always indicator of t is equal to 1 times y1 is equal to indicator of t is equal to 1 times y. So I've used both. Consistency, regression estimate. Both together with our property of expectation allows me to substitute y by b star. Okay, so it's no problem. Now you again condition on x, right? So what you can do is you can again condition on x, and there's an indicator here. Once you condition on x, this will be a probability of t is equal to 1, right? So you can actually get this thing out, essentially, right? So you will actually have b hat plus probability of t is equal to 1, which is precisely pi star of x, by pi hat of x, times b star of x minus b hat. This is what it is. Okay. You massage this. You can actually show that this is nothing but 1 minus pi star of x by pi hat. Okay, so this is only the doubly robust estimator. There is another expected value of y1. So I'll have to subtract b star. I forgot about it. Another expectation. So you subtract this. That's given, if you manipulate this, basically you have b minus b hat out, take it out. You will get 1 minus pi star by pi hat times b hat of x minus b star. So here it becomes very clear. If this is consistent, the bias goes to 0. If this is consistent, the bias goes to 0.
Yeah, I did not understand how did you get pi star of x in place of indicator t %. What did you do?
Yeah, so here it's a joint. So here, once I've substituted it, everything is a joint distribution of x and t. Now you condition on x, then you do expected value of this. This is a constant, this is a constant, this is also a constant. This is also a constant because pi hat of x. The only thing random variable is t. Indicator of t is equal to 1. So you get pi of. I mean, I skipped steps, but the more important thing is you will get this expression. Every single time in this business, you just do out your expectation, you will go through. So here, what it shows is that my bias is actually a product of some sense, the bias in either pi star or b. Of course, this is not exactly pi hat minus pi star, it's some sort of a normalized version. But normalized version of pi star times the absolute difference, sorry, the difference between b hat and b star. So it says that if one of them is small, you are good enough. At least one of them should go to 0. It's okay if this is very bad, right? If this is very high, no problem. But if at least one of them goes to 0, you actually have an unbiased estimate, which cannot be said about the high system. Right? Because if I get the pi hat wrong here, there is just no way that the bias is going to go to 0. Right? Similarly, if I get the pi hat wrong here, it's not going to go to 0. If I get b hat wrong here, this thing is not going to go. But the question is, in any estimation, you don't know which thing you are, what you can estimate well and what you cannot estimate. Therefore, this, in some sense, consistency sense, we would have a stronger estimate. That's all I'm trying.
This is why it's called doubly robust.
That's why it's called.
Because one of them, if it is good, then it is good.
And in some sense, some variant of doubly robust estimator gets the minimax variance, I think. Okay, and that was proven by a paper which I cannot recall. I don't want to again quote only half authors and not give credit to every one of them, but there is a paper that actually shows. Okay, so this ends the story here. Now let's actually go to the promised confidence interval for IPW estimate. So it's okay, I'll erase that part. Is it IISc?
So 1 minus pi star by pi and the other, these are product within the expectation, right?
Yes. Product of this times this.
So you can't split the expectation.
No. But when n tends to infinity, one of the terms going to 0 will make sure. So you can do Cauchy. Yeah, it can blow up. Of course, the blowing up has to be controlled and all that. The point is that it shouldn't go up to infinity. Yeah, sure. If it doesn't go to 0, and then if you have b hat minus b star going to 0, then it's okay. Of course, if one thing blows up and the other thing doesn't, then it's a change. I mean, if you have an estimator where something is blowing up when n tends to infinity, then you shouldn't be estimating at all, right? Like you have some, so you have definitely done something.
One thing that estimator, shouldn't the right hand side be divided by the number of samples you are?
You are right. Sorry. Yeah. I meant, yeah. So when you take expectation, you will actually get these. Fine. This is strong log by n goes to here. It's okay. Now let's go to IPW. I think I have messed it up by not writing it properly. So let me erase and write it properly. That should look. I missed a term here. So this is expected value for x. And same thing carries out. And this is equal to final. Hence doubly robust.
If there is a quantity that I want to estimate and there are two estimators which are consistent in different regions, then can I always, is there a generic way of coming up with it?
So convex combination, that's one trick. Is there any other trick? I don't know. I mean, the question is very general, yes, but here it's a bit more specific. It says that I can always import a sample without estimating, without regressing. This is computationally, I mean, assuming you have estimated the propensity well, there's no regression here. But if you have any other estimator which is approximate, you can always do a doubly robust version of that. That's what we have said so far. But it works very specifically with importance sampling. You are asking the more general principle. I can only think of some weighted combination.
Weighted combination won't be consistent, right? If one of them is.
If conditioned on x, so okay, when I say consistency, I mean in a stronger sense. When n tends to infinity, b hat of x goes to this conditional expectation, x almost sure. So over the measure over x, I don't have a non-trivial set of non-zero measure where these two are different when n tends to infinity. So I'm making a very strong consistency statement, right? In that particular case, it's okay. You can have w of x times one estimator plus 1 minus w of x times the other estimator. If all of them are consistent point-wise, then the whole thing will be consistent. So I don't think it's an issue there. The issue comes when you are saying only when the expected value is consistent, then yeah. But I'm talking, think of this as a function. I learned a function and I'm saying the function is consistent. That only means that, yeah, it has to tend to the conditional. Okay, so now let's go to IPW. Let me erase that and I'll only have this estimator. In fact, the most important point is the estimator is that 1 over b blows up. Okay, so I'll just derive a very generic Hewitt estimation bound and then apply this. That's all. So I won't go into just writing indicator and 1 by pi all the time. So
what are you going to do?
what's the concentration here?
Concentration bound for this estimate.
Okay, I just wanted to say that the estimator of interest is nothing but if I give a bunch of samples xi, I have the indicator of t is equal to 1, xi comma ti, right? So ti is equal to 1 divided by some phi hat of pi given xi multiplied by yi. So I have yi. So this is a tuple of samples that I have. That's from the table. I simply form this estimator and that's my estimate, correct? Now, the expected value of this is something. I'm only going to derive a concentration bound, the deviation. So I'm not taking into account whether pi hat and pi are the same. So I'm going to derive an estimator where E hat converges to its expectation, which may have bias depending on whether pi hat is good or not. So let's make a simplifying assumption that pi is known, and this is my estimate. Okay. I'm going to only find out what is the probability of E hat minus E greater than epsilon. What is the concentration? Yeah. By all let's keep missing it. Yeah, sorry. So let's simplify this, right? All that matters is that you have IID samples x1 till xn, right? And the expected value of x squared is less than sigma squared. That's all I know. I have n samples. There's nothing else that's known about this distribution. Yes.
So assuming pi is perfectly.
Yeah, pi is perfectly. Or the useful thing is I only care about I shouldn't have used say an m hat enter m hat, the expected value of n, whatever that expectation. I'm just going to derive concentration. I'm not going to worry about it. So here so one more important thing. If you are working with contextual matrix, right? And if you have some past policy that you've used, and you want to just know if I treated everybody with treatment equals 1, what would happen? This is exactly the estimator that you use, where policy is known. So in off policy estimation, this is one of the basic building blocks. Only that in off policy estimation, you would be interested in deploying your own policy. Correct, right? But in this case, it's a uniform policy. If you have another policy, you can put pi of whatever that policy is. And that would be an important sampling estimator. So it's a very general thing what I'm trying to do. So this is off policy. Okay. I'm just asking you, I've given a bunch of data. If I want to plot a new policy, in this case, just a uniform policy, what would it be?
Yes. The context is exact.
Context is exact, yes. I mean, even in this case, context is pre-treatment variables. It's all exact. So before treatment, you should have looked at some xi and decided the treatment. There's a probability with which you would have chosen the treatment for exploration purposes. I don't know. You would have logged it. You would have said, okay, I have chosen. This person came, that person had this context. I recommended p equals 1, but with this probability. I'll just log that probability. And they have like months and months and months of data. Somebody comes new and said, okay, I want to uniform. I want to deploy only the same treatment on the whole population. Can you tell me what it is? This is the simplest. The generalization of treatment.
When you say off policy, you mean changing pi, right? Like you generate data from some pi and you want to estimate it for some other pi.
Right.
That's what
I mean by it. But the most important thing, again, I want to stress, it doesn't occur too much in practice, is that I never claimed that T was decided based on Xi. I only assumed ignorability. So the normal measure change argument, this is more general than that. So in causality, what really matters is the very simple ignorability condition. If the potential outcomes are independent of the treatment given some features, that's enough. I only need to import a sample with respect to that. If you give me a new policy, I only need to know the conditional distribution with respect to this set of features. I don't really care what else you looked for your new policy or your old policy. It's not important. The fact that ignorability holds implies you can assume as if you only looked at X and decided what it was. So it's a very subtle thing. It might look like a measure change argument, but it's much more general than that. This you cannot derive from probability right on neighborhood variable. You need to go through this conditional independence argument to make sure that potential outcome that you care about is derived. Just want to make that point clear. Yes.
That was sort of precisely my question.
Okay.
So you want y to be independent of t given x?
No. I never wanted to say. So ignorability. So is the thing focused here?
Y1 to be independent of
Y1, Y0 to be independent of t given x. This does not imply necessarily that one looks at x only and decides the treatment. Of course, this is true. This is not true. Okay? Somebody could have looked at some other X, but suppose somebody is able to tell you that ignorability will hold for this feature. That's all I need for importance. So it's a little bit fun. Yeah.
Yeah, sorry. So the question was that you want that, but in a bandit context, you are specifically changing the treatment based on Y1 and X, the combination. And is that why you need off policy? Like, therefore, on policy is not possible.
I mean, your past data. There's nothing I'm going and doing now. I'm just doing an estimation.
Yeah. So
that's
therefore, something like UCB will not satisfy ignorance.
UCB, first of all, pi being, so for that particular xi, UCB always picks a deterministic. So UCB alone will not, no, it will not satisfy positivity. That's the problem. But let's say you did Thompson sampling, then you would. Or let's say if you did something else, sorry, epsilon really, for example, then you will have a non-trivial positivity under which this is true. UCB alone is a bit tricky because at that particular point, you've seen all the data and there's a deterministic UCB indices that you have. Therefore, you picked one.
So my point was, can I decide treatment based on Y's?
No, you should not decide. No. Treatment is never based on Y's. Here, potential outcomes is independent of T given X. If you remember the three graphs I drew, maybe I should draw it here again. X, T, Y. This is the world, actual world. But you're talking about some imaginary worlds. What are those imaginary worlds? You force the treatment T is equal to 1, and you have Y1. And you have another imaginary world for T is equal to 0, right? What we are saying is the world is in such a way that if I construct this world, Y1 is independent of T given X, like all the confounders are blocked. You may ask, how would you know? Right? We will come to that later. I will tell you some very interesting recent work where you don't need to know the whole causal graph or anything of the sort. Very limited information. You can actually certify that X actually blocks and satisfies these conditions. But for now, we will assume again ignorability holds, and someone gave you that these features satisfy. The only point I wanted to make was that this is so obvious for someone from probability because it's just random nitrogen derivative. But it's not just that. That's all I'm trying to say. Okay. Now let's come back to this. 1 over phi can be unbounded. The only thing I want is that the variance is bounded by sigma squared, right? And for an unbounded variable with only a moment constraint, I want to just derive constellation. Okay, so I'm only given the variance constraint. So what is the inequality that you know if you are given only variance constraint? Chebyshev inequality. I have to use it somehow. So this is how you start using it. So you have n samples. You divide it into k groups. So I'll name the k groups as the following. So this is x11, x1m, x21, x2m, and so on till xk1, xkm, where m times k is equal to n. So let's just assume that n is divisible by k. This is a simple assumption, just to not pain ourselves too much. And we must basically divide all the IID samples into k groups. Randomly, doesn't have to be. Just shuffle maybe, and just take the first m into one group and so on, and then you will have k groups. Okay. Yes.
You are assuming the variance is counted or the second moment is.
Yeah. So okay. So let me simplify this. Let's say the expected value of x is equal to 0. Just put it there. I'm only worried about the deviation. Right. So in fact, let me be more clear instead of making assumptions. Mu is finite, of course. Mu is finite. Right? So you divide into m groups. Then what you do is you create a simple average out of every one of them. Okay. So here Z1 is nothing but summation x1 m divided by the total number. right? So similarly, Zk will be Zkm divided by m.
So is K the number of groups or M the number of?
M is the per group number of samples. K is the number of groups. K is the number of groups. So if you look at one row, it's all the samples in the group. I'm indexing them by K. Okay. So M is the number of samples in a group. So for each group, I create this mean vector. Very simple. Okay. So far I'm done with it. Then what you can show, what you do is that you simply take the median of Z1 till Z2. And that's your estimator. That's it, right? That's your estimator. Now, what I want to prove is that the expected value of mu hat minus mu greater than or equal to, let's say greater than 4 sigma, sorry, sigma square root 4 by m is less than or equal to e to the minus k by 8. Might look like a handful. I will slowly now substitute things and make sure this is all reasonable. Okay. So here, what I'm trying to do is that I'm trying to derive a deviation, and the deviation is proportional to what would be a standard deviation had this been a Gaussian. The 4 is a suboptimality, but it is 1 over square root 10. So this looks much like a sub-Gaussian bound. Of course, m is the number of the samples within a group. So instead of n, I have m. So now I need to get an n here, right? But I also need to take care of the confidence. So what I'll now do is that I'll set this confidence to delta, less than delta. So what I'll do currently here is k will be set to 32 log 1 over delta. Okay, let me be clear, maybe 16 is enough. So let me actually look at that notes just to make sure. Okay, so this is sufficient. So 8 log, I mean, you can change these numbers, not very important. So 8 log 1 over delta, if you substitute it back here, m is n by k. M is n by k. Okay. So you do that, you'll get 32 log 1 over delta divided by n. So the estimator is finally mu hat minus mu greater than sigma square root 32 log 1 over delta divided by n, the total number of samples. That is less than or equal to basically 1 just delta. I have to prove this, I prove that, but if you have this result, then this is true. Now, I think in Gaussian, I believe you can get 2 here or some very optimized constant. So it was an open problem, whether you could get to the 2. And there's a long line of work trying to reduce the square root 32 to something close to 2. Okay, there you need to go and play some magic with these estimators. You need overlapping groups and all of that. Okay. Okay, but that's not the open problem I was referring to. I'll come to the open problem I'm referring to. But there are a series of works trying to basically get the best constant here so that it would almost match the sub-Gaussian. Okay, and the verdict I think is still out.
Yes, there is an M hat, which was that estimator. That original estimator that you did.
Yeah.
Now, mu hat. Now, what is the relation between mu hat and M hat?
No, the M hat is this is the estimator.
So are you claiming that somehow the median and that average over there are the same? Is that a claim?
No. What I'm saying is I wanted an estimator so that I can get a sub-Gaussian tail bound. That's how I started with. My estimator is you divide it into k groups, do mean in each one of them, and once you take those things, do median of them. And that's my estimator. I'm claiming that now I have a sub-Gaussian tail bound.
The next between and was that IPW estimate, right?
So what I'm trying to say is that all your xi's are just these numbers.
All your there is a xi there also. Now you are.
Yeah, so I overloaded the thing.
Now I see.
Okay, so I'm sorry about that. Yes, maybe here I'll make it some other CI context. Right. So I'm just saying that each one of these terms are my xi's. The only thing I know about them is that the second moment is bound. By the way, there is a more clever estimator. If you are not able to guarantee the second moment, but you can actually guarantee 1 plus epsilon moment or 2 plus epsilon moment, there is a very interesting generalization of these bounds. They are called Ketone type estimators. Gabor, Lugosi, someone else. Let me actually look through the notes to see who the. Okay, so I don't have it with me. I think Lugosi and someone else, Lugosi et al., they actually have a monograph in 2019 that says something about heavy-tailed mean estimation. And in one of the sections, you will basically see what I'm proving here. And there are many more estimators trying to tighten and stuff.
So if y is bounded, then you have a bounded second.
No. It depends on 1/pi, no?
And pi is pi star.
Pi star, yeah. But we don't know how low the probabilities can get. Right? So it could have a very heavy tail. Yeah, sorry. I want to write indicator.
So M hat was the average, right? This mu hat is like the median of like average over these multiple k groups, right? So M hat is not exactly mu hat, right? But mu hat and M hat are related. So you first get a concentration bound for mu hat. Now you're going to extend it to M hat.
No. The expected value of M hat is mu. I'm just providing an alternate estimator which has a good concentration around the expected value. I'm not claiming anything about. Okay, so let's prove that. There are two tricks. I'll just
Estimated value of M hat is mu from like consistency or non-zero bias.
No, there's no bias. So here, this estimator will have bias because I'm taking the mean. They themselves don't have bias, but I take the median of a bunch of numbers which have no bias. I have no idea what they will be. So I can't say anything.
So my question is then why you okay? So this
because I need to get a concentration, right? So very tight concentration. So you need to pay.
Right. So now you want to then also bound the difference between mu, which is the expectation of M hat,
Correct.
and the actual.
Correct. Okay, maybe I should have mentioned that. Right? So expected value of M hat is equal to mu. Okay, this I should have said. So I am disposing of M hat because they are high variance. So I'm coming up with some alternate estimator saying that it has almost sub-Gaussian concentration. I mean, you'll have some Gaussian if you can improve on the 32, but I won't improve on the 32. I'll just prove this bound. And there's a lot of literature trying to like get to the very tightest thing. And there are variants of these ideas essentially. Okay. Now let's try to prove this. Okay, proof. So what we'll first prove is that probability of each of the ZIs having the same deviation is less than or equal to 1/4. Okay, this is not very difficult, just Chebyshev's. I'll come to that, just write down later. But suppose you have this, right? Then the next question, because you have 1/√10 deviation. Usually, if you have subversion, 1/√10 deviation will have exponential stuff. But here there's nothing, so you only have constant probability. Okay, this can be proven. Okay. Now, what you need to show now, look at the median. What's the final estimator? This is the median. Now you are saying you care about mu hat minus mu to be greater than the same sigma times square root of 4/n. Right? Now this is a median. Mu hat is a median of a bunch of things. Right? Now, if the median has to be greater than something, so median minus mu has to be greater than something, it must mean that for half of the zi's, this must hold. The argument clear? So I'm looking. So look at only the lower tail. I mean, the other tail you can justify yourself. The median is above half the numbers. It's below half the numbers. So that's what the definition of median is. And there's a more exact definition. I'm not going to go into it. Just look at the lower tail. You are saying mu hat is greater than mu plus sigma times something, right? But mu hat is a median of k numbers. So half of them has to be greater than this. That's by definition of median. Okay. So at least, so this event implies at least k by 2 of zi's basically satisfy zi minus mu is greater than sigma square root. Clear? Okay. Now, what we have said is that suppose we create an indicator function and let's create a Boolean variable out of this. There are k Boolean variables. Now, I have said that the bias of any one of them is at most 1/4. They are independent, by the way, because the groups don't overlap. Okay, so they are IID. I have IID Bernoulli variables. Each one of them has bias 1/4. Okay, and I'm saying the total sum is at least half. The bias is at most 1/4, but if you sum all of them, there is at least half. Right? So there's a very large deviation. But now we are back into Bernoulli concentration, which is exponential. So then so this implies that the following event, that the summation of bi divided by k minus the expected value of b, because they are IID, it'll have some expectation. But I know that the expectation of each one of them is less than 1/4. But for this to happen, for this to actually happen, for at least k by 2 of the zi's has to be 1. This indicator has to be 1 for k by 2 of them. So this sum is already half. This is at most 1/4. So at least this has to be greater than 1/4. This event implies this event. This implies this event. Therefore, the probability of this event is upper bounded by this. Okay, so so this statement says probability of the expected value of b is less than or equal to 1/4. Now I want half of them to be 1. So my empirical mean is at least half. Right. The expected value is less than 1/4. So at least the deviation must be 1/4. So the probability of mu hat minus mu greater than sigma square root 4/m is actually less than or equal to the probability that summation bi by k minus expected value of b is greater than 1/4. This is all Bernoulli bounded variables. K of them are there, right? And I need a deviation of 1/4, right? If you work out the Hopkins inequality, you will just get e to the minus k/8. Because it will be 2k epsilon square. Epsilon square is 1/4 square, 16, 2 cancels, we get an 8. Right? I am not doing all of that, but yeah. Right? This is good. Now I've shown already, like the final probability is less than or equal to e to the minus k/8. This is what I wanted to show. Shown, and you substitute k is equal to whatever that 8 log 1/delta, then you get this. Okay. I claimed it's a sub-Gaussian tail bound, but note one more thing. In usual mean estimation, whatever delta it is, and I can scale my the confidence region as function of log 1/delta, I should get probability approximately proportional to delta. But the estimator never changes. However, here you can't just state this. You have to understand that the groups basically scale to the confidence that you actually care about. They don't have any flexibility. So question obviously is it even possible to get a flexible tail, at least for some reason? I don't know the answer to this question. So that's one question. Let me tell you the next thing. Yeah, go ahead.
Sorry, one step back again, but the second statement, at least k by 2 of the GIs are have bi equal to 1. Why is that?
Because so I'm looking at this event. Suppose this event is true.
Yeah.
This event, say, okay, just look at the lower tail. This lower tail.
Oh, right. If
mu
the
hat
event is true. So if that event is true, then this is bounded by.
Yeah, the lower tail is true. If the lower bound is true, again by the median argument, half of them would be below that stuff. That's also true because it's a median. And therefore, in either of the cases, this indicator function has to be given as sigma. Is it clear?
First open problem. You said
Okay, so first open
depends on the confidence, the data itself.
Yeah, so first of all, you can tighten this if you don't have a open problem that you can't easily type. You need more interesting ideas, and people have done some typing. The second important problem is that it's not a uniform tail bound. Depending on the confidence interval I want, I need to change my groups. I need to go back and re-estimate for estimate. Think about a million samples. Somebody tomorrow, your boss comes and says, oh, what is your confidence? Okay, 0.05. I don't like 0.01. You go back and do the same estimation. That's a problem. That's one issue. The second issue is that nobody told you what sigma is. It's only one parameter that I assume. You have to, technically speaking, it would be great if you can substitute sigma by sigma hat. That's not an estimator. But then you may need to assume something more, because if you want to estimate sigma hat very well, then some fourth moment or something like that has to be bounded. That might be true. But with some additional assumptions, if I can estimate sigma and then plug it in and have an empirical estimate, so that there is no assumed quantity in anywhere, basically, that would be remarkable. We know that such a thing exists for Bernstein estimators, for example. It's called empirical Bernstein. I don't want to go into empirical Bernstein because that's not the point of the thing, because we have a heavyweight variable, so the Bernstein won't apply. But in the Bernstein case, if you have bounded random variables, you have a second moment bound. You can empirically estimate the second moment, plug it in some fashion, and with some looser constants, you can still prove a concentration bound. So you get a constant confidence interval just purely from data. Here, the confidence interval is not purely from data. There is an assumption here. So who is going to tell you that the expected value of 1 over p square is going to be upper bounded by sigma square? Somebody has to give you that bound. But that bound is crucial because it will dilate your confidence interval. So the interesting open problem is that as a purely a function of data, can you actually get an empirical Bernstein type estimate? Might be not even possible. Maybe you need more assumptions here. Apart from the second moment, maybe you need some other conditions. But that's largely open, and that would be super useful.
So even if you assume higher moments are bounded, this problem is still open.
I don't know exactly what's known, but I think nobody has an empirical version of this system. That's all.
Yeah. So now the K groups instead of M samples each group is M1 and median is like the weighted medians of the things.
Yes, so
kind of bound.
Correct. You might get similar, but you need to make so the problem would be the translation here. If each one of them, so if the final thing, first of all, you need to figure out what the final thing should be. Maybe some weighted version of the M1s, I don't know. Then that implies that some weighted version of the GIs has to be greater than whatever stuff. Then yeah, you're right. You're sort of in the same book. But I don't know how to do that translation. So you want to say that
I just randomly partition and
do the weighted.
So it is difficult to analyze, but we don't know it doesn't work.
It doesn't work or anything. The other more important thing is why should the group be disjoint? They can be slightly correlated. It's not going to hurt your booleans quite a lot, right? Turns out that when you dilate this a little bit, you get some extra benefit. That's exactly what gets rid of this 32 to something much smaller. But you need to adjust accordingly in many other ways. Right?
Is it known it only helps in those constants?
Yes, there is a lower bound that says there's a 2-point lower bound. So in the minimax lower bound sense, for every sigma square, I'll attain the sigma square by using 2 points, literally one on the other. I'll change the probability mass. It's like a Boolean, like a dichotomous support, like we call it that way. So there's a dichotomous variable for which up to the constant, the scaling is minimax alpha. So which means there exist distributions whose variance is at most sigma square. They are in fact they have a 2-point support or a finite support from what I remember. And there's a minimax lower bound that says that except for the constant, there's some constant. This is true. This has to be true. Like it has to be greater than that. Okay. So it's known that except the 32, you cannot do better than for this particular assumption. Okay. So in some sense, if you have bias 0, so for this particular type of problem, this is sort of the best concentration you can possibly get.
So that confidence interval, let's say I get a bad dependence on delta. Even then, the problem is open. Like now I create an estimator which doesn't have any dependency on delta, but I'll get a slightly worse.
No, but you need, confidence if it's very, very small, if you have error event whose confidence is small, this has to scale with delta, right? There's no other way.
Right. So instead of log 1 over delta, I get log square 1 over delta.
But
those depend, even those are fine.
Those are fine. Yeah, but if it's log square, people are trying to reduce the square root 32 to 2 here. So I'm trying to understand what's the play of getting that dependence on log 1 over delta to log square. Confidence interval does dilate, right? Because, for example, if I have 0.01 delta, you're already talking about, it's actually log 2, right? So you're log E actually. So you're already talking about a 3 or something. So you're already like dilating it by a factor of 3 or something like that. But yeah, those things are over.
Even as a first step.
Yeah.
Even if you get some wrong dependency on.
Yes, that is fine. But the more important thing is I don't want that dependency on an unknown variable. Can I actually do it as an empirical work? For Bernstein estimators, such things exist. Okay. So I referred to a paper by Yuan Botu. I said something that people must read for counterfactual optimization. There they discuss this empirical Bernstein estimate. They do a clipping. So they actually make the variable bounded and they analyze that. But if you have Bernstein estimators, there you can substitute empirical variance and it still works. Like the whole thing works with some modifications. We don't know how to do that for.
Independently, I derive concentration for confidence interval for sigma.
Okay.
Can't I just substitute that here and get some?
But if you want to do that, even mean itself is so much painful. It comes from the same random variable. You're trying to estimate the variance of this at the second moment. We need stronger conditions, but my guess is that estimator won't be any more less noisy than this estimator. So you need to do, if you look at the empirical Bernstein, how it's derived with a slightly different technique. It's not about just doing some concentration and substituting that. It's a bit more, I think Chava et al. Have a paper on this. But what we don't know yet is how to actually do empirically. Currently, what people will do is, if you have 1 million samples, they will basically try to estimate this, and then they'll say, okay, that's my bound, and I'll just go with that. The problem is you don't even know the mean. So you can't even estimate the variance. You will estimate only the expected value of square, which is horrible. And you will get a dilated confidence. You have wider confidence interval than that is necessary. But you would ideally want to be the tightest. It's not very clear how to get. This is very important. If you make progress on this, a lot of off policy things will become very interesting. So there is one paper by again the group DeepMind, I think. What they said was that something like what I'm asking is possible, but for the lower tail, but not for the upper tail, which was a little bit strange. You can say that the effect is at least blah, but you cannot say anything more about the upper tail. Okay. And they have the style of bound that I'm actually talking about, but it's a bit different. It's not about just substituting sigma. They take a bunch of x1s to xn's, and their bound is a function of all these data. That's it. On the y's. Sorry, it's only a function of x1s to xn's. So basically, they take the pi and the y, and then they come up with some very interesting estimators. But it's a deterministic. So the confidence, the tail bound holds for a fixed set of data. And you can derive a concentration bound that the mean can be within this with some probability. But that's a I mean, those things are there. But how do you not go beyond data but still try to estimate the yes.
So I think this estimator median of means is very generally applicable. Nothing was specific to the IPW.
Yeah.
What
Yeah. People use it in bandits, heavy tail bandits.
and therefore, like this sort of method should be used everywhere. Does it always improve?
Yeah,
either
it's a very standard alternative. So otherwise, you could do that. Variance is controlled. They are bounded and it's controlled. The only problem is the bias. So if the bias is not too large, and if you have enough number of samples, that might be a better estimator actually. People have analyzed, self-normalized about something estimator.
And somewhere are we assuming that all of these are similar distributions? So, for example, IID samples.
It's all IID, right? Like in the data side. People are IID, I'm assuming.
Because if group one is estimated from, if samples one is estimated from group one, domain one, and so on, there might be a bias for you.
Correct. Then it's a separate problem of handling. But even the bias correction, if it's an important sampling variant, again you will fall back to this estimator because the estimate is very general. All I need is some variance bound. Once the variance is finite, I just give you a form. Basically, it excludes distributions like what Cauchy type of Cauchy, even the mean doesn't exist, but it's.
Streaming algorithms used like it's AMS estimator for FA, and if it is median of means. Now the streaming algorithm.
I see.
Everywhere, you just need to show constant. Like the success probability is constant and you can boost it to.
Yeah, I think see this trick, medianization trick a lot. Here, the only thing is that if you have variance bound, you can do Chebyshev, and then on top of it, you create Boolean variables and do it. That's all I'm trying to say. Not saying
People start with there.
Yeah. So this I have observed at many places. I think in randomized algorithms, you have this. You probably have then you do median majority, and then you analyze that, right? So it's the same.
But the weighted I've never seen. Is that something which?
So I don't know of any weighted estimator. But there's a lot of work to reduce the that's the implications of this thing. If you substitute 2, I think it's some C is minimum. So you really working at the constant. But the more interesting question is if sigma by itself must be estimated before you estimate this, then that's the more interesting, useful problem. You provide the pi of 1 or pi of t given absolutely. All I did was a t. Okay, so I have 15 minutes. I actually thought that I would finish earlier today, but I have a few more things to say. So let me quickly go and say all of those things. Okay, so this is all about average treatment effect on the entire population. There's something called individual treatment effect. So I've not even gone to that yet. So if a patient comes with those features, I would like to know for that particular patient, what is the treatment effect? That's something that I want to know. So it gets into the territory of counterfactuals. We will use the ignorability condition. And I'll convince you that conditional average treatment effect is the same as the counterfactual in this case. And we have pre-treatment variables. I'll just stop it at that. When I go to the Perlian stuff, you will get the full-blown counterfactual stuff on why it is very different from all these things. So let's go into the treatment because that's a more interesting problem. Okay. And there are a bunch of estimators that were proposed, and we will slowly go through each one of them. I will start with this very famous paper. By the way, the reason I'm going through this paper is because this is sort of implemented everywhere. It's called X-Learner, S-Learner, and T-Learner. And if you go to any package, it's implemented, right? So I'm going to go to that. So the paper is by Kunzel et al. It's a PNAS paper in 2019, okay? From Bickel and Vinew's group. Which part should I erase, right? So should I erase that part? Start. So meta learners for ATE, individual treatment effect. We will argue approximately, because the formal argument of what I'm going to say needs a little bit. Get introduced it on 3 lectures now, but I'll do henceforth. But I'll give you a flavor of why counterfactuals are a more difficult quantity. But in this particular case, it becomes very simple. We will say that the individual treatment effect, which is a counterfactual going beyond potential outcomes, this is equal to the conditional I would say that in expectation, conditional average treatment effect. Okay, actually, that's strongly doing this. So we call this K. The estimator is nothing complicated. It's the same thing that you're seeing without the expectation outside. That's all it is. But the thing is, it implies something a bit more complicated under the ignorability criterion. So we'll go to that first. Then we will talk about some different estimators that have been proposed for ITE. If you have regression boxes, what all can you do? Like some very similar to the question that you asked. Okay. I won't go into like proofs of the sample complexity. I'll just describe those estimators. Okay. Then we'll go to the next lecture. We'll go to representation learning for IT. Then we get into neural nets and the modern world. Okay. Yeah. So still it's in conventional statistics. Okay. So what is individual treatment effect? Right. So let's go back to the table. So I have X, I have T, and I have Y. I said there are these two imaginary columns. This is Y1, this is Y0, and these are called potential outcomes. They don't have any other formal interpretation except that there are just two sets of columns. And Y is related to these two with a consistency equation. That's the only thing that we have here. Nothing else about what those mean and all that. Right? But okay, and there is this U, which I said is all the unknown variables, all the exogenous variables, all your genetic factors, all your past history, everything from where every part of you came from, all that is in this particular thing that defines an individual. But I can only capture some of your characteristics, and that's a pre-treatment variable, right? But what do I actually want, right? If a person comes in, basically you get one row in this table. Okay, you see one of them. Ideally, I would like to know for this person, if I had shown a different treatment, what would the treatment affect? That's what you actually want to know. So that is actually given by Y. Here, notation has to be very clear. So I'll try to use all the variables and so on. And then I'll show, first of all, this is not estimable, but something slightly more, slightly weaker version of this is estimable, but not in general, but under the ignorability and pre-treatment case, it's equivalent to K. So there are three quantities. So let me first tell you the first quantity that cannot be estimated, which is Y1 of U minus Y0 of U. This is all I want. How would you get it? You will not get it because first of all, you don't even see the whole U. You only see the X part of U. Right? So if I want to know for this particular individual, what would have happened had I treated that person differently, how would I be able to estimate? I won't be able to estimate. Okay, what is the next thing you can ask? Okay.
Given X, what's the expected value?
Given X, what's the expected value? That is something that you can ask. So here, expected value of Y1 of U, condition 1, X is equal to X. Okay, but this involves quite a lot of stuff. So let me explain what it means. Let's say there's a person who came to me in, let's say I'm a fictitious doctor, a very bad one for sure, even fiction. And let's say a student comes to me, or a person comes to me and says, well, there's a problem. and I treat the person with some particular thing. Okay, let's say unfortunately the person gets into coma or he or she dies, right? God forbid, but yes. What you're asking is that had I treated with a different drug for that person, what would have happened? Okay, now that is U. That's a U version. This version is asking a slightly different question. It says that, okay, let's depersonalize the person a little bit. The person came with a medical record. So there was a U and there was an X. But for all the people who came to me with an X, if I had intervened differently, what would have happened to them? That is basically a conditional counterfactual. I mean, I'm just making it, this is a counterfactual, just making it more. Now, what is the problem? The problem is the table has a P of U. But condition on X, right? The exogenous variables will get conditioned. So you are actually already operating as P of U given X. First of all, I don't even see U. Furthermore, the marginal distribution has been shifted to something else, conditioned on X. Stage Y1 of U, which also I can compute because it's a function of some imaginary quantities. So it's almost like saying that if a person died, what is the effect of the drug on that day? It's a very legitimate question. You're talking about a counterfactual. Okay, so you take the dead person, you look at all the people who died, their exogenous variables will get conditioned in some complicated way, and then you pass Y1 of those U's, an average under that conditional distribution, and you need to get this way. Okay, so this is
You had data for most treatment, the counterfactual would be what would have happened if I gave the treatment,
yes,
and vice versa. That if I had given a treatment, that's what would have happened if no treatment was given. Is it both of the cases considered as counterfactual?
yes. What I'm trying to say is, okay, so I'll come to that. So this is definitely a counterfactual, but this is easy to estimate because from ignorability, you can actually show that if you condition on T, this guy actually becomes independent of the treatment, basically, right? So we will call this conditional average treatment. Okay, so this is the treatment effect on the individual. This is the conditioning on X is equal to X. So this is actually conditional average treatment effect. It's also called a counterfactual. So it's not a complicated counterfactual for the following simple reason that the intervention, so X may have been treated with T equal to 0 or 1. Okay, so X might have some X's might have been, so maybe there are two rows, X is equal to X, here also X is equal to X, T is equal to 1, T is equal to 0. Okay, now when I say I'm conditioning on X, I'm conditioning on both these people. Okay, but I only see Y1 only for one of them, but not for the other. But I need to average over all of them. Okay. So this is conditioned on X is equal to X. What is the treatment or the treatment effect, basically? So that is conditional average treatment. The most important point is that when I condition on X and when I go to the counterfactual world, nothing basically changes in the sense that the U doesn't get conditioned anymore other than X. It's a sort of very important point. So what I say was that, so you have X comma U and you have treatment T and you have Y, right? Now, what I'm trying to say is if ignorability holds and it only holds in the pre-treatment regime, you can manipulate this. And if I want this, I can actually show this is nothing but the expected value of Y given T is equal to 1, comma X is equal to 1. It's okay to take all the individuals conditioned on T is equal to 1 and X is equal to X and just simply average the outcome. And then positivity. Positivity also holds. Right? So this is just simply, I mean, this is somewhat an interventional quantity. I'm asking what's its interventional quantity for all the people whose medical record is X. So I want to average treatment. This is a conditional average treatment effect. It's also a counterfactual, but it's not a very complicated counterfactual. Okay, the one you asked is a very complicated counterfactual. I'll come to that. So When you condition on X, there is some P of U given X, and this gets averaged. Right? That's the only complication. Still a complication, but I proved to you that under ignorability, this can be solved. Okay, that's one thing. But what he asked is something far more complicated. What he asked was the probability of y1 of u conditioned on x comma t is equal to 0. Right? This says the person got treated by t is equal to 0. Also, that you know. Conditioned on that, now I go back and change the treatment is equal to 1. What will actually happen to that person? This is a more complicated counterfactual. Because I am saying P of u gets conditioned further by x comma t. This is what I write. So we will estimate conditional average, basically treatment. Is that clear?
Just from this table, you can't estimate y1 for this p equal to 0. Okay?
Which table?
This left side table.
Yeah. You cannot estimate for this row. Yes, that I said first. The conditional version you can estimate. I have not told you why this is true.
That is harder because if there was no U, everything was observed, then they both are same.
Yes, that is still the same. But the main problem over here is that because of the U, it's a bit difficult to understand what this would. Because now so the problem is that you are changing something downstream of you are conditioning on something downstream of my treatment, including myself. So the thing gets conditioned very non-trivially, and then you need to do stuff. But this is very simple. Because the treatment change from t is equal to 0 to 1 does affect the u. But when you condition only on x, that doesn't get affected because the treatment is decided at weight. Okay, so there's no additional conditioning apart from p of u given. So, yeah.
Why these expectations are the same? You are not explained. I thought it follows from ignorability condition.
Correct. That's all I want. This follows from ignorability. This one is a bit complicated. You will come to that. Yes.
So for the second one, it's easier because you can have rows in your table that contain that value. But for the y1 given t is equal to 0, you will never observe that.
Yeah, you will never observe that thing, and it's a very complicated list. We will come to that a bit later. But I'm going to only estimate the conditional average treatment. Okay. Is that clear? This is very important. But now, having said that, now I'm going to say one more thing. By the same ignorability, condition on x and t, y will never depend on the choice of the treatment. So this is equal to the expected value of y1 of u conditioned on x. Ignorability is very powerful. So going from here to here requires ignorability. That's only going from conditional interventional effect to the conditional expectation. Now I'm saying something more complicated here. This row, as he pointed out, doesn't even exist in the table. But because of positivity and ignorability, conditioning does not matter because I already told you that y1 is independent of any factual treatment conditioned on given x. So for all those people who got treated t is equal to 0, this conditional expectation is same as the marginal conditional expectation overall. That is why it is possible to estimate. Okay. So we will later on find out when ignorability holds and all that. That gives rise to when such counterfactuals can be estimated. But this is a very powerful criterion. We went to the counterfactual level, imaginary rows, which completely have not been. The whole estimator itself is on imaginary rows. This is only star. Under ignorability, that is equal to the conditional expectation of the interventional thing. Okay, some of them you know, some of them you don't know. But then again, because of ignorability, again, and under consistency, this is equal to expected value of y. Okay, so this is what I care about. And this is finally what I get. This is y given t equals 1 x. So whether you got treated or not, the regression is a good estimate. Ultimately, the final bottom line is very simple, but under ignorability. So ignorability is a very non-trivial condition. Is it clear what I'm saying? So ignorability hides so many things. That's all.
So effectively what you said is someone asked for a unit where the treatment never was there, you'll find an equivalent person who had the same X,
Correct.
who will have that
Correct.
treatment and say it's the same.
Precisely, and that is called matching. And we will come to the next how do you use this exact point that you made. But I looked at only the untreated. What would have happened had they been treated, given particular X, but only from this group. You need to find an alternate person from the treated group who had a similar X and maybe substitute, and that's a good estimator. In the limit when KNN gets a consistent estimator, this will be a good estimate. That's exactly what this is saying. So this notion of finding a pair who's similar to you in all respects is exactly what this principle is saying under ignorability. And we will make this into a nice neural net architecture and all that, and we'll draw a connection to representation. We will come to that later. But
can there be different ways of clustering nearest neighbors in the
yes, so there's a long line of work. Weighted KNN, and then KNN plus regression, matching, and all that. So the people have done all sorts of stuff.
all over Causality.
Yeah, over this economics and statistics, there's a lot of literature, so I can't go through all of them, but I'll go straight to 2017. There's a very nice paper by Uli Shalit, Johansson, and David Sonntag on how to use this thing that you said to actually come up with a representation level. Okay? But before that, let's go to meta. So all I have said is that individual treatment effect is very complicated, depending on the treatment status, is same as a conditional average treatment effect, which is same as the conditional distribution under treatment is equal to 1. But for this, you require positivity and ignorability. So I'll end here. Next time I'll go to meta learners. So I mean, once you come here, it's just a question of what regressors you want to use and how many different ways in which you can estimate them. Is that clear?
Because of all that, too many meetings. But I think I over one.
Yeah. So all I'm saying here is that when you conditional t is equal to 0, you get condition non-trivially, but because of ignorability, it saves you. So you get to the conditional average statement effect. Then you come to the observational volume. So you have gone 3 ladders down. Sorry, 2 ladders down. Silent.